Ever had your application grind to a halt? Or worse, corrupt data, and you stare at the logs, seeing deadlock found or lost update detected? It's a nightmare, right? If you're building anything with a database, understanding transactions and locks isn't optional, it's survival. Without them, your data is a ticking time bomb, and your users will feel it. By the end of this video, you'll not only grasp these core concepts, but also have practical strategies to prevent deadlocks and protect your data's integrity, even under heavy load. The atomic unit. What's a transaction anyway? Okay, so real talk. A database transaction is basically a single, logical unit of work. Think of it like a bank transfer. You debit one account, then credit another. If one part fails, the whole thing needs to fail, or your bank's numbers get seriously messed up. This all or nothing idea is at the heart of what makes databases reliable, and it's encapsulated by the famous ACID properties. Honestly, if you forget everything else, remember ACID. Atomicity means it's one indivisible operation. Consistency ensures data moves from one valid state to another. Isolation means concurrent transactions don't mess with each other. And durability? Once committed, that data is there to stay, even if the server crashes. The Wild West. Nasty concurrency problems. Okay, so transactions sound great in theory, but the moment you have multiple users hitting your database at the same time, things get messy. Really messy. Without proper handling, you open yourself up to a whole host of weird bugs that are super hard to debug. This is where concurrency problems rear their ugly heads. Let's talk dirty reads. This is when one transaction reads data written by another transaction that hasn't been committed yet. If that second transaction then rolls back, your first transaction just read data that never actually existed. Wild, right? Then there's non-repeatable reads. Imagine reading a row, doing some work, and then reading the same row again within the same transaction. But its value has changed because another transaction committed an update in between your reads. This can lead to some truly baffling logic errors. Then we have phantom reads. This is similar to non-repeatable reads, but it's about rows appearing or disappearing from a result set. You run a query, then another transaction inserts or deletes rows matching your query criteria. And when you run the same query again, you get a different number of rows. Super frustrating. And my personal pet peeve, lost updates. Two transactions try to update the same data, but because of improper locking, one transaction's update simply gets overwritten by the other, as if it never happened. This frustrates me because it's so insidious. Often, you don't even know data was lost until much later. Taming the chaos. Database isolation levels. This is where isolation levels come in. They're basically different strategies databases use to manage concurrent access and prevent those nasty bugs we just talked about. It's a spectrum, a sliding scale between maximum concurrency, fast but risky, and maximum data integrity, safe but potentially slower. Some devs swear by one, others hate it. Here's my take. There's no silver bullet, only trade-offs. At the bottom, we have read uncommitted. This is like the Wild West. You can read uncommitted data, meaning dirty reads are totally possible. It's rarely used in production. And honestly, I think it's mostly for niche reporting where speed trumps absolute accuracy. Next up, read committed. This is the default for many databases, like PostgreSQL and SQL Server. It prevents dirty reads because a transaction can only see data that has been committed. But you can still experience non-repeatable reads and phantom reads. It's a good balance for many applications. Still with me? Good, because this next part is where we turn theory into actionable strategies. Understanding deadlocks is one thing, but knowing how to prevent them is where you become a database wizard. Moving up, we hit repeatable read. This prevents dirty reads and non-repeatable reads by ensuring that any row a transaction reads will look the same if read again within that transaction. MySQL's InnoDB uses this as its default. Plot twist, phantom reads are still possible here. For the ultimate safety, we have serializable. This is the strongest isolation level. It guarantees that concurrent transactions will produce the same result as if they ran sequentially. No dirty reads, no non-repeatable reads, no phantom reads. But, and this is a big but, it comes at a significant performance cost, often through extensive locking, which can lead to more deadlocks. Use it only when absolutely necessary, or for very short, critical transactions. The gatekeepers, database locks. Okay, so isolation levels are the policy, but locks are the mechanism. This is how databases actually enforce those rules. Think of locks as little bouncers at a club, deciding who gets in and what they can do. The two main types are shared locks and exclusive locks. A shared lock allows multiple transactions to read the same data concurrently, but no one can write to it. An exclusive lock means only one transaction can access that data for both reading and writing. No one else can even read it until that lock is released. Locks also operate at different granularities. You can have a row-level lock, which is incredibly precise, locking just a specific row or rows being modified. This is generally preferred because it allows high concurrency. Multiple transactions can work on different rows in the same table without blocking each other. Then there are table-level locks. This is a coarser approach. It locks the entire table, preventing any other transaction from reading or writing to any part of that table. This is faster to acquire, but severely limits concurrency. Hot take. If you're using table-level locks for anything other than very specific, short maintenance operations, you're probably doing it wrong and killing your performance. The ultimate freeze, understanding deadlocks. All right, this is the big one, deadlocks. You've probably heard the term, maybe even seen one in your logs. A deadlock occurs when two or more transactions are each waiting for the other to release a lock, creating a circular dependency. Neither can proceed, and they effectively freeze each other. It's like two cars trying to cross a single-lane bridge from opposite directions, and neither is willing to back up. In databases, deadlocks usually happen when transactions try to acquire locks on resources in different orders. For example, transaction 1 locks row A, then tries to lock row B. At the same time, transaction 2 locks row B, then tries to lock row A boom. Instant Deadlock. Both are waiting for a resource the other holds. The database's job is often to detect these and kill one of the transactions, rolling it back so the other can proceed. This is why you sometimes see deadlock victim errors in your logs. It's the database saying, sorry, someone had to go. Strategy Guide. Preventing and handling deadlocks. Okay, the good news is you're not helpless against deadlocks. The best strategy is prevention. First, always acquire locks in a consistent order. If you always lock resource A then resource B, you eliminate a huge class of deadlocks. Second, keep your transactions as short and sweet as possible. The less time resources are locked, the less chance of contention. This means committing frequently, not holding transactions open while waiting for user input or external API calls. This is probably the most impactful thing you can do right now. Even with the best prevention, deadlocks can still happen, especially under extreme load or in complex systems. So, detection and handling are also crucial. Most modern databases have built-in deadlock detectors. When one is found, the database typically picks a victim transaction, rolls it back, and allows the other transactions to proceed. Your application code needs to be ready to catch these deadlock victim errors and retry the transaction. Implement exponential backoff for retries to avoid immediately hitting the same deadlock again. It's not glamorous, but it's robust. Let's recap. Transactions are atomic units of work governed by ACID properties. Concurrency issues like dirty reads, non-repeatable reads, and phantom reads are real threats. Isolation levels offer a spectrum of protection, with trade-offs between speed and data integrity. Database locks, both shared and exclusive at row or table levels, are the enforcement mechanism. Deadlocks occur from circular dependencies, often due to inconsistent lock acquisition order. Prevent deadlocks with consistent lock ordering and short transactions. Handle them with retries and exponential backoff. The key takeaways: always define clear transaction boundaries in your code. Choose the lowest isolation level that meets your data integrity needs to maximize concurrency. Implement consistent lock acquisition order across your application. Design transactions to be as short-lived as possible. Build retry logic with exponential backoff for deadlock errors into your application. If this helped you understand something new about keeping your databases robust and bug-free, consider supporting the channel. Every bit helps keep these videos free for everyone. Drop a comment with your thoughts on your most frustrating database bug.